my voice as I narrate the slides. I'll go ahead and tell you now that my goal for the entire course is to tell a story. So if you're looking for a lot of the details and facts, I'll try and use my voice to emphasize what I really want you to take away, but ultimately I want you to learn about everything that you listen and see in every lecture for the semester. So I want to start out with this because the title of the class is Natural Resources, Economics, and the Environment. What does that actually mean? I want you to train your eye on each of these 4 photographs. These are dioramas in a museum, and all I want you to see right now is how different the existence for these early humans was compared to us. These photographs, these dioramas, don't represent any humans on planet Earth today. We have evolved significantly, as each of you are aware, technologically and socially, from this period of our past. So I've got a question up at the top and a statement. I want you to take out a sheet of paper and I want you to make a list of the natural resources that you think the individuals in these dioramas used. And by natural resources, I want that to be intuitive. Everything that you see in these photographs that they would have used in order to make their lives better. So what do we see? We likely see animal hides that are used for clothing, here on the man, here on the woman. We see the boy here has something, most likely an animal hide that he's using as clothing. We see on the right over here, we have a stick that's being used, most likely to try and make fire. We see on the bottom right over here, 2 men, both with clothing, both with spears, and the spears they're trying to kill this animal here, which would be a food source, and then also the hide would be used as clothing or as a way to make objects to carry water or to cook with. We see on the bottom left, we see these huts, thatched roofs. We can see somebody here carrying on a stick 2 what were likely prehistoric buckets. And all I want you to take away is that if you were to sit down and make a list of all the natural resources that are being used by the people depicted in these photographs, that number is orders of magnitude less, meaning far less than the natural resources you and me and everybody in our global society consumes today. So I want to introduce the class by walking you through the history of human use of natural resources or human consumption of natural resources. Now, if you go back to middle school, if you went to school in the state of Michigan, and most states I think have a similar curriculum, it's probably about 6th grade that you might have a memory of looking at this. In 6th grade, you typically take a social studies class that involves history. And I can tell you, having 4 kids who have gone through 6th grade, it is history mostly through a European lens. Big problem with our K-12 education system in the US, in my opinion. But what I want you to focus on here is on the left-hand side, we've got time, where BC here represents before Christ, or as you'll see in my lecture slides, I'll use BCE, meaning before the Common Era. So if we think of the year 0 as the start of the Common Era, anything prior to the year 0 or older than the year 0 is before the Common Era, or BC, BCE. And all I want you to take away here, I don't want you to memorize anything in the middle. I just want you to focus on the words Stone Age, Stone Age, Stone Age, Stone Age, Stone Age. And what we know from anthropologists and archaeologists is that humans spent the better part of the first few million years of our evolution, our existence as we think of humans today, in the Stone Age. And the Stone Age is referred to aptly because the only tools that we used in nature were effectively stones. And we used stones to kill animals, We used stones as rudimentary tools, but we didn't use any of the elements in the periodic table that today are embedded in the fabric of modern society. The use of metals starts up here at the top of this timeline with the Copper Age that gave way to the Bronze Age that gave way to the Iron Age. And I'll use these dates again, but it's important to remember here that the Copper Age, the Bronze Age, the Iron Age occurred in sequence. The Copper Age was first, then the Bronze Age, then the Iron Age. And what I want to do now is walk you through how humans evolved from the Stone Age to the Copper Age, and then the Bronze Age, and then the Iron Age. Now, when you were in 6th grade, if you were like me or you were like my kids, you may have been bored almost to death by this part of social studies. So I'm hoping today I can make it a little more exciting. So the first place that we find evidence that humans evolved from the Stone Age into what we can think of as the post-Stone Age, or the Copper Age, the Bronze Age, the Iron Age, is by reading the Old Testament, the Torah, or the original 5 books of the Holy Bible. And I'll tell all of you, if you haven't read it, you should. Not from the perspective of a belief in a single omnipotent being that some people refer to as God, but read it because it's a part of history. And if you read the Old Testament, I'll read this quote from the book of Job. Men know how to mine silver and refine gold, to dig iron from the earth and melt copper from stone. So what is contained in that statement that's of interest to this class? The words silver, gold, iron, and copper from stone. So during the Stone Age, humans were physically using stone as a tool. And as humans evolved from the Stone Age, first to the Copper Age, and then the Bronze Age, and then the Iron Age, humans figured out how to actually extract the pure metals, silver, gold, iron, and copper, from stone or from rocks, where stone and rock are synonyms. And if you read the Old Testament, you find that gold, copper, silver, tin, lead, iron, bottom center, and mercury are specifically identified in the Old Testament. And these are referred to as the metals of antiquity. And these metals changed humanity forever. The ages here, or the numbers, again where BCE stands for before Common Era, so before the year 0, these numbers represent the approximate age based on archaeological studies around the world when humans began using each of these metals. In terms of the very first metal, gold, by about 6,000 BCE, so approximately 8,000 years ago, and copper about 4,000 BCE, so about 6,000 years ago, when humans transitioned from the Stone Age to the Copper Age. So we have evidence for these metals of antiquity, and when we evolved from the Stone Age to the Copper Age, I want to explain how and why we did it. You're looking at a photograph here of what we call native copper or elemental copper. So my cursor here, I'm tracing out what you can think of as a beautiful shiny piece of copper metal that you might think of as a copper penny or a copper coin or copper piping that you may have seen in your house or apartment that's used to bring water into your house or apartment. And humans were able to find native copper like this, which they could use stones to hammer into tools that made their lives easier. And among the first places on planet Earth where we have evidence that humans did this, this is a map of modern-day England, and in northwestern modern-day England, just west of the city of Liverpool here, there's a place called Great Orme. And if you travel to Great Orme, right here in northwestern England, you see caves that look like this. And initially, you might think the caves are natural, but they're not. These caves are prehistoric copper mines. And the only reason that these caves exist is that humans, when they first settled in this area, at least 6,000 years ago, they noticed that much of the rock in this area had, as you can see in these photographs on the right side of your screen and the lower left, this beautiful green color or green patina. And that green color was an indication to the early humans in this area that within this particular rock was the metal copper. And if the humans could dig into the rock, they could extract that copper and use that copper for a variety of purposes. So the humans in this area 4,000 or 5,000 years ago, they dug tunnels, dag isn't a word, they dug tunnels that ran for miles beneath the surface. And they would have done this initially with very crude stone tools. And then as they learned to extract the copper and make tools out of copper, they used the copper plus stone tools to expand the caves. And the copper was used both locally, and copper was also exported. That's the first time I'm going to use that word in this class, export, which means that the copper was physically located in this area of England that we call Great Orme. It was physically extracted from the rock. You can see here is a sample in the top right, somebody holding it in their hand. And that copper was then manipulated with stone tools and subsequently with copper tools and exported elsewhere. And that elsewhere means that we had trade. So the copper is sourced at Great Orme and it's exported at this time to other places in England, other islands in Britain, and across what we call today the modern English Channel into continental Europe. Here are a set of photographs of ancient copper tools. Some of these are from the Old Kingdom in the early 6th dynasty in Egypt. And what I want you to see here is that all of these tools have very specific shapes if you look at the photographs. And what was significant about the transition from the Stone Age to the Copper Age was that humans discovered native copper, meaning that it is pure copper metal, not bonded to anything else. Pure copper metal, 100% copper, and they were able to figure out or to deduce that they could physically manipulate that native copper and make tools. And making tools allows humans to accomplish tasks faster than in the absence of tools. That's why we create technology. And these ancient copper tools were a major technological advancement. And as a result, they literally put places on the map. So now if we move from prehistoric England and Great Orme, now you're looking at a map of a part of the ancient Middle East. So here we have on the lower left the Mediterranean Sea. Anatolia is here, the modern country of Turkey. We would have Greece off here to the left side of your screen, the Black Sea up top, the Caspian Sea up here top right. And then we have Mesopotamia, which was also a focus of 6th grade social studies. Everybody, at least everybody who went through school in the US learned about the Tigris and Euphrates rivers, and we learned about Babylon. What I want you to focus on, I'm going to trace over with my mouse right here. Here we have 1, 2, bottom center 3, right bottom 4, 5, 6. Each of these represents a mine or a place on planet Earth where the metals that are indicated were present at the surface of the Earth, so that humans in that area could actually see the metal at the surface as they did at Great Orme, and then dig into the rocks or dig into the soil at the surface and extract those metals. And if we look at the map, here we have Kultepe, we have silver Ag and copper Cu. If we look up here at Erzincan, we have tin Sn and copper Cu. And I only want you to look at this because I want you to see that the transition from the Stone Age to the Copper Age, where humans figured out how to use copper and subsequently other metals, It put places on the map, and it increasingly led to trade routes among different groups of people throughout the known world. If we then look at this particular image here, this is a relief, and all I want you to see here is we have a depiction of 3 people, and I want to ask you what you think they're doing. If we look here, each of them has one hand up by their mouth, and they have a second hand, as you can see the arm extended down here, and they're depicted holding what was likely, you can think of it as a pipe or a straw. And what they're doing is they're blowing air through the straw down into a fire, almost identical to what you may have done or you may have seen somebody do when we blow into the bottom of a fire in a house or a campfire. We're blowing oxygen into the fire because a fire is nothing more than the reaction of carbon in wood plus oxygen, which produces heat and carbon dioxide. In this case, they're adding oxygen to the fire to increase the temperature of the fire so that they can do what we call smelt, which is a process that allows them to extract metal from rocks. The transition from the Copper Age to the Bronze Age, and here I've got just a depiction of bronze top left. Bronze is the 3rd place medal in the Olympics, and this is a medal from the 1980 Olympics in Moscow. The Stone Age, we use stone. The Copper Age, we use copper, pure copper, 100% copper. And then humans transitioned to the Bronze Age. And bronze is not a metal of its own composition. Bronze is what we call an alloy. And I want to walk you through how humans discovered the ability to make bronze. And the reason that humans decided to make bronze was that it is harder than copper. So if you have 2 metals and you can combine them to make bronze, that bronze is harder than copper. But first I want to show you a video to emphasize something that I know all of you learned at some point in middle school or high school, which is that when we have a metal and we think of a metal as solid and we add energy to the metal, that metal will absorb the energy. In this case, it's a blowtorch. So here we've got a blowtorch, and that blue indicates a flame. And what do you see happening to the metals? The metal is softening, meaning that the metal is physically transitioning from a solid plus energy to a liquid. And what was significant about the human transition from the Copper Age to the Bronze Age is that humans figured out not only how to liquefy metal, but how to mix more than one metal together and then pour that metal into what we call casts to make tools and objects that were much harder than copper. So we could take that metal, which started out as a solid, add energy to it, it became a liquid, and notice that we could now pour that metal into a mold or into a cast, and the metal transitions from liquid back to solid. Sorry about that. I know I'm going to make mistakes throughout the term. I'm okay with that. And now that metal, which started out as a solid, we added heat, it became a liquid, we poured that liquid into a mold, we now have that metal as a new shape. So this is a new way of making tools and making other objects that allowed or was essentially the defining point for humans to transition from the Copper Age to the Bronze Age. So that's all I wanted you to see in this video, is that we start with metal, the metal is solid, we add energy, what you can think of as heat. When we add energy, the atoms of that metal literally absorb that energy. The atoms start vibrating, moving. When they're in the solid, they're effectively motionless. We add energy, they start to move, and they melt And when they melt, they produce a liquid of the same composition. And now we can pour that liquid into a mold and we can create new objects. We did not do this during the Copper Age. So during the Copper Age, humans took native copper and would use stone tools or copper tools to pound the copper to make tools and artifacts or different objects, but they didn't melt the copper. The reason they didn't melt the copper is that the temperature at which pure copper or native copper melts is higher than the temperature of conventional fires. So if you think of a conventional fire, you go and buy some wood, you put wood in the fireplace, you ignite that wood begins to combust. Carbon plus oxygen equals energy or heat plus carbon dioxide. If you look at the left here, it's a list of different metals with their melting points or melting temperature in degrees Fahrenheit and degrees Celsius. And I don't want you to memorize this for all of the metals. I simply want you to focus on the melting temperature here for copper is almost 2,000 degrees Fahrenheit or almost 1,100 degrees Celsius. And on the right-hand side, the same data for a variety of metals are just presented as a histogram. So here would be copper, and you can see that copper melts at about 1,100 degrees Celsius. Early humans could not get fire that hot, so they couldn't melt copper. That's why all of the copper tools were the result of simple manipulation, banging on that copper to make different objects. The transition from the Copper Age to the Bronze Age occurred when early humans figured out that they could actually take the metal copper and they could physically mix it with another metal that had a lower melting temperature. And by physically mixing copper with a second metal, grinding those two metals together, they could create a liquid, and that liquid would be created at a temperature lower than the melting point of copper. So I'm going to play a video now and walk through what happens. And I just want to highlight that what we're doing is starting with two metals. In this case, we have one metal here on the top right. We have a second metal here on the bottom right. And let's watch what happens. I'm going to kill the video audio there just to watch what happens. This person is recreating how early humans made bronze. So they started out with copper, and of course they wouldn't have had a digital scale that worked with batteries, but just go with it. So they're making a mixture of about 90% copper and 10% tin, two separate metals. So this 90% copper, 10% tin, and they're putting that into a fire. Here we can look through the top of the furnace and we can see the energy, at least the color tells us that there's a lot of energy or heat. And you can see something almost identical to what I showed you in that last video. You can see that those solid metals that were added are now transitioning from solid to liquid. Importantly, the two metals, as they transition from solid to liquid, are creating a liquid alloy. Alloy is a mixture of two or more metals. And these liquids, or in this case liquid alloy, is used for what we call casting, where we can actually pour it and we can make tools. So you see here more of the tin is being added, and that ratio of 90% copper to 10% tin was likely found by trial and error. It's not an accident. And I'll just fast forward through here, and I want you to see what happens. On the bottom here, we've got a wooden box, and it's filled with dirt or clay. And the top here, we've got our melted mixture of copper and tin, and that melted mixture of copper and tin, the alloy, is being poured into a hole in this clay. And notice that as it's poured, it's losing energy. So energy flocked to cold. An alloy or liquid alloy, which was liquid when it was poured into the space within the clay, it loses energy to the clay, and watch what happens when the clay is now broken apart. This is what we refer to as casting, where humans create a shape within, in this case, clay, and by pouring the liquid alloy into the clay, notice now that that liquid alloy crystallizes back to a solid, and importantly, remember we started with solid copper and solid tin at a ratio of 90% copper to 10% tin. That melts. We then pour that liquid into this open space that we've created, and it crystallizes or solidifies, and it takes on the shape of the hole that we created within this clay. A process that we call casting. Now, why does that happen and why is it important? So let me walk you through this diagram and follow my cursor so I can help you make sense of this. So on the right-hand side over here, we have copper. Copper has a melting temperature of 1,084 degrees Celsius or 1,984 degrees Fahrenheit, which means that if you have pure copper, you have to heat that copper up to this temperature in order for the copper metal to transition from solid to liquid. On the left-hand side, lower left, we have the metal tin, and the metal tin has a melting temperature or melting point of 232 degrees Celsius and 450 degrees Fahrenheit. Now, what does that tell us? It tells us that the metal tin has a much lower melting point than the metal copper by about a factor of 5. So early humans realized that they could melt tin in conventional fires, think campfire or a fire in the fireplace. Early humans knew that they could not mix copper, and it's thought by archaeologists that some accident allowed early humans to recognize that if they took tin and mixed it with copper, so we have a diagram here with the y-axis showing us temperature in degrees Celsius, so 0 degrees Celsius here at the bottom left, and getting hotter as we move up the y-axis. If we start with pure tin, we can melt that at 232 degrees Celsius. But notice that as we physically add copper, meaning now that we've got a physical mixture of tin and copper, as we increase the mass percent copper, which is shown on the x-axis moving from left to right, as we take pure tin and we increase the amount of copper that we mix with tin, we have 10% tin, 20%, 10% copper, 20% copper, 30% copper, 40% copper. Here would be 50% copper, 50% tin. So as we move from left to right, that video that I just showed you was for a physical mixture of 90% copper and 10% tin, which would be right here on the lower right. And notice that by physically adding 10% tin to copper, the melting temperature of that mixture is lower than the melting temperature of pure copper. And the reasons for this I'm not going to get into right now, but I invite anybody to chat with me during office hours and we can discuss those details. What I want you all to take away is that this black line shows us the division between solid underneath and liquid above. So that as we start with pure tin that has a melting temperature of 232 degrees, and we start with pure copper that has a melting temperature of 1,084 degrees, if we move along the black line, that black line indicates the temperature at which a physical mixture of tin and copper, shown down here on the x-axis, will be a liquid. What was significant that allowed us to transition from the Copper Age to the Bronze Age is that by adding only 10% tin to copper, the temperature at which that mixture melts was relatively easily achieved by blowing oxygen into conventional fires and adding charcoal. And charcoal is exactly what you think it is. It's the same type of charcoal that you use to grill. So by mixing charcoal with copper and tin and blowing oxygen into the bottom, they could create temperatures that were high enough to melt that mixture of copper and tin. They then create a liquid, and that liquid can be used to cast tools or other objects. And that's how the Bronze Age started, which is pretty amazing. Where did the Bronze Age start? Lots of disagreement in the archaeological community. There is a lot of evidence that it started in the Middle East, that it was started by the Hittites, shown here. This is the outline for the Hittite Empire about 3000 BCE. There's also evidence that the ability to create bronze, an alloy of 90% copper, 10% tin, that there was also bronze discovered in China and possibly other places around the world, including parts of Africa and parts of Europe. But remember, the key here is that humans have gone from the Copper Age, where all we could do is pound copper to make tools. We could not melt it. But now by adding about 10% tin to copper, we could blow oxygen into the fire, and we could create a liquid, and that liquid we could use to make tools. And bronze tools are harder than copper. That's why humans wanted to make bronze. It gave you a military advantage. So if your army could be outfitted with bronze, you could, all things being equal, defeat an army outfitted only with copper. Bronze beats copper, like rock, paper, scissors. Bronze wins. And what we see is this rapid transition beginning about 3000 BCE, depending on the area of focus, where humans moved from copper to bronze. And the reason? Bronze is harder. So what did that drive? It drove trade. It drove exports. It drove imports. If we look here at this map, where I'll show you the legend on the bottom left, the legend here, the red indicates tin deposits. So look at the map here, and let's go over here to Asia. All of these areas in red in Asia, here we have in Africa, we have here in the Middle East, we can come up here to Europe, and then over here into Spain and Portugal, parts of modern-day Germany, France, and then we can look over here in the modern-day English Isles. Each of these red circles or ellipses was an area where humans could find tin on the surface of the earth, and they could then extract that tin and they could export it to other areas. And the reason we know that that tin was exported is that if you look at the map here of the Eastern Mediterranean, so here we've got the boot of Italy, here we've got Greece, here we've got modern-day Turkey, or then Anatolia. Here we have modern-day Egypt, Israel, Saudi Arabia. There were almost no tin deposits. And by tin deposit, I mean there were no rocks at the surface of the earth that contained tin. There's evidence for a couple of small deposits here in eastern Anatolia, but the evidence indicates, at least to archaeologists, that humans were moving around Europe and Africa and Asia to find tin, to bring it back here to the Eastern Mediterranean, where the tin was mixed with copper, and each of these yellow dots is where we find tin objects and bronze objects in archaeological digs. So we're starting to get a sense of, as we transition from the Stone Age to the Copper Age to the Bronze Age, trade. And if we look at ancient maps, this is a map by the Greek philosopher Strabo, and it's a map that he drew of Europe about 20 BCE. So we're now much later than the Copper Age and the Bronze Age, but just stick with me for the purpose of illustration. We've got here his depiction of the boot of Italy here, roughly in the center, and then Europe, the Iberian Peninsula here, Spain and Portugal. We've got the Straits of Gibraltar here, the Scylla and Charybdis, and then we move across to Morocco and Northern Africa. And this mare internum would be the Mediterranean Sea. And so Strabo tells us in his map that if we look carefully at the upper left portion, or I guess I should say left center portion, the ancient Greeks had identified what we now think of as the modern British Isles, so England and Ireland and Northern Ireland over here, that they named them the Cassiterides, Cassitterides, and cassiterite was the word for tin in ancient Greek, kassiteros, and to the ancient Greeks, these islands were referred to as the Tin Islands. So the ancient Greeks were literally sailing through the Mediterranean Sea, out the Straits of Gibraltar, up and around to get the cassiterite and bring it back to Greece over here off the map on the bottom right to mix with copper, and the copper they sourced locally, but they had to move away in order to get the tin and bring it back. And we see here in a map that depicts trade routes for tin in the time period from roughly 1950 to 1850 BCE. Don't get lost in all the words. All I want you to see is that each of the triangles here represents what archaeologists have demonstrated were human settlements. So again, we've got lower right is the Persian Gulf, upper right is the Caspian Sea, top left and center is the Black Sea, and on the left-hand side over here, we've got the Mediterranean Sea, and then we would go down through what today would be the Suez Canal into the Red Sea. All of the triangles represent places, right, along the Tigris and Euphrates rivers, and all of the dots represent trade routes. And all of these dots specifically represent trade routes for tin. Humans wanted tin, and they could not get it locally, so they had to develop trade routes to source tin from faraway places and bring it back to the Middle East, the Levant, Anatolia, ancient Greece, to mix with copper to make tin. And we see in maps by Strabo and others that the ancient Greeks would either travel by ship and then across land. So here we have the rivers that they could use to help travel across Europe, or they would travel out here through the Straits of Gibraltar up and around to their Cassiterides or Tin Islands. So trade is evolving. And why is trade evolving? Because early humans recognized that bronze was harder than copper, and in order to make bronze, they had to have both copper and tin. And since they could not source tin locally here in the Eastern Mediterranean, in Greece or Anatolia, or in most of the Middle East, they had to move out and they had to bring back the tin. And we can think of this as a diffusion of metallurgy. So again, big picture, if we read the Old Testament, the original books in the Torah, we see that we have gold is the first metal that humans were using. We then have silver, we then have copper, and we have tin. And it's copper plus tin that starts to drive human trade routes around the Middle East, around Africa, around Asia, throughout Europe, and likely other parts of the world. So what metal led them to discover England, meaning them, the ancient Greeks? It was the metal tin. And you can travel today to the southwestern portion of England. So here on the inset on the right-hand side is an area known as Cornwall, England. And if you travel to England, you can actually see the rocks that the ancient Greeks physically dug out and took back with them to Greece. So here we have on the lower right, we've got a man's head for scale. And everything that he's looking at here, all of this open space, would have been completely filled 3 and 4 and 5,000 years ago with rocks that look like the photograph on the right, where we've got a hammer for scale, and all of this rock, all of the black that I'm tracing over, all of that black is a mineral that we call cassiterite. And the ancient Greeks, and following the ancient Greeks, the Romans, and throughout the Middle East, the Hittites would seek places like Cornwall, England, the cassiterides. They would find rock that is enriched in tin. They would extract that rock enriched in tin and take it back to their home cities where they would mix it with copper to produce bronze. And this is happening elsewhere. So again, most K-12 systems in the United States, it's a very Eurocentric or European-centric focus on history. But if we look, for example, in China and other parts of Asia, we also know that the ancient Chinese, independent of anyone in the Middle East or Europe, at least archaeologists think independently, also ideated the creation of bronze by mixing about 90% copper with 10% tin. So this is a photograph from the Metropolitan Museum of Art in New York City. And if you look at them, I just want you to get a sense here of how intricate they are. These are from the Shang Dynasty or the Western Zhao Dynasty, and I apologize if I'm butchering the pronunciation there. But they represent bronze that was created between about 1046 and 771 years before the Common Era. And I love this kind of art, honestly. I love it. If you've ever had the chance to go to the Metropolitan Museum of Art in New York City, they've got a phenomenal art display or collection of bronze antiques. And I just want to ask you this one question here. How were these made? And I'm going to show you a video that gives you a sense of how copper plus tin mixed in that magic ratio of 90% copper, 10% tin. We physically mix them, we add charcoal, we blow into it with oxygen. That allows the copper plus tin to transition from 2 solids to 1 liquid. That liquid is now an alloy that is a mixture of 90% copper, 10% tin. And here we have a depiction of how in ancient China they used that mixture. I'll play the music, probably nicer than my voice. How they used that mixture to create these objects. So I'll stop it here for a second. This is a bronze object, okay? And as the text here shows, nobody can know exactly how the ancient Chinese made this, but we're pretty sure this is close. So how the heck do you make this beautiful bronze object hollow in the... The first thing they would do is they would create a model made of clay, literally a model made of clay or dirt. They would allow that to dry. Then they would put more clay around it to create a box. Then they would cut that box open. Let me back up for a second. So they first create the mold out of clay for the object that they want to make out of bronze. So there's no metal here. This is all clay. And then after that's allowed to dry, so think literally about how mud dries to become hard, they then create a box. They cut that box away, and notice that on the inside now of these 4 pieces of the box, what do you see? You see the shape of this animal. So they've essentially now made a mold and when they take the clay animal away and they put back together the box, remember on the inside of the box is now open space, and that open space is the shape of the animal that they had initially made. They would take that box, they would drill holes into it, And then what do you think they do next? They would pour into those holes this liquid mixture of 90% copper, 10% tin, and as they pour that liquid into the holes, imagine we have X-ray vision and we can see into that box to see the interior of the mold. That liquid fills all of the open space. And remember that that liquid is now going to lose heat or energy to the surrounding clay. And that liquid is going to transition from liquid to solid. And by breaking off the clay on the outside, you now have a bronze object. And that bronze object now has all of the properties of bronze. I love this stuff. Honestly, if you're ever at a museum and you get a chance to see some of these artifacts, what truly amazes me is that humans were ideating this 4, 5, 6,000 years ago. I've got another video here. I'll just play it. Give me a chance to take a sip of water. So again, look at the object and notice how intricate the engraving is on the outside. How do they make it? They use this process called piece mold casting, which is identical to the last video, where they first make the object that they want. They then artistically surround the object with either images or letters. And notice now when they then put the clay on the outside of it and they allow it to dry and pull it away, notice on the inside of the mold, we have the negative relief of everything that has been very carefully carved on the object. They would then refine the decorative text on the inside, remove the object, put the clay mold back together, drill these holes in the top or bottom, 90% copper, 10% tin, physically mix them, melt them at a temperature that's slightly lower than the melting temperature of copper because we've added tin, pour that liquid mixture in, remove the outside, and look at what we have. To me, this is just awesome. If you did this today, I'd be wildly impressed. Imagine if you had a party and invited friends over and said, we're going to cast some bronze. They would literally love it. You got to be laughing right now, but I'm pretty sure most of you would find that pretty sweet. Now, what does that do? We go from stone to copper. Copper is used to make tools. Tools allow work to be done by humans more easily than stone tools. We then figure out, the collective we, how to alloy tin plus copper. I've mentioned the concepts of export. We now have imports. We now have trade. And these are just a couple of snapshots. If anybody here is interested, these are the articles. You can get these up here at the top at these web links, totally free. But what we start to see during what geologists call the Holocene, and all I need you to think about is the Bronze Age, is we now start to see, as we move from the Copper Age, where we started to have trade routes evolve, to the Bronze Age, where we need tin, and tin is not as abundant as copper in many places throughout the Middle East and Asia, Europe and Africa. We now start to see people move. And the reason they're moving is to get access to the metal tin and the metal copper to make bronze. And the reason they want bronze is both to make ornamental artifacts or jewelry, but also they wanted bronze because it could be used in warfare. And the empires that were able to make bronze earliest, including the Hittite Empire here on the map on the left side of your screen, those empires flourished between the period of about 3000 BCE to 1200-ish BCE. Then something happened, right? Then it appears that the shit hit the fan for a lot of areas, a lot of cities throughout the Middle East and the Eastern Mediterranean Sea, on the Greek peninsula here, also Italy, not shown but off to the left, parts of Anatolia or the Hittite Empire, parts of the Assyrian Empire. And if you look at the legend here, all of the little fires are not campfires. They indicate cities that were destroyed. So one of the things that happens is we go from the Copper Age to the Bronze Age, and then there is what we call the Bronze Age collapse that occurred between about 1200 and 1150 BCE. And by collapse, as I said, literally the shit hit the fan. There is evidence in all of these cities depicted here on the left, and evidence shown here on the map on the lower right. These X's all indicate cities that were completely destroyed around 1200 BCE. And then up here at the top right, this is a photograph where we're looking only at the base of what would have been a palace at Tiryns, which was a huge Greek palace that was destroyed at the end of the Bronze Age, during the Bronze Age collapse. And there's a significant amount of research being done by archaeologists, anthropologists, and geologists, often working in concert with one another to try and figure out what happened. What we see is almost overnight, the Mycenaean kingdoms, the Kassites of Babylonia, the Hittite Empire in Anatolia and the Levant, the new kingdom of Egypt, Ugarit, and the Amorite states, poof, just completely destroyed. And if we look at archaeological evidence, there's some evidence that suggests there were these nomadic tribes referred to as the peoples of the sea that may have invaded and destroyed these cities. And I think that's the prevailing hypothesis and wisdom today among archaeologists and anthropologists. There is also a lot of evidence in the geologic community that a succession of severe droughts or climate change in the Eastern Mediterranean occurred at exactly that time between about 1250 to 1100 BC. And a lot of that evidence comes from drilling into the soil or ancient lake beds in places like are shown here on the left-hand side of your screen. This is Cyprus. So here we have the island of Cyprus. And this little box here in the lower part that I'm tracing is the Larnaca Salt Lake, which is right here by Larnaca Bay. So again, if we look at the global map, we've got Africa, we've got the Middle East, we've got the Mediterranean Sea, and the island Cyprus is here. And what geologists have done, specifically geologists who focus on understanding climate in the ancient past, is they drill into the sediment there. And on the left-hand side, I'm tracing over, this is literally sediment that has been drilled and pulled out of the ancient Larnaca Salt Lake, which is completely dry now. And they look at, for example, pollen, and they can see in the pollen over that time period of about 1250 to 1100 BCE that the climate dramatically changed. And as we are now seeing, even in the year 2021, we know that climate, as it changes, both now and in the past, that causes human migration. And if you want to read this study, it's a fantastic study. You can also get this one free of charge here on the lower right, and I'll post it in Canvas. That led, in addition to the search for tin plus copper to make bronze, it led to human expansion, geographic expansion. And I'm just showing you one example here, where if we start by looking at the top right, this area that I'm tracing out here, sort of in the brighter peach color, represents an area that was dominated by the Yamna culture. And Yamna, if you look here at the lower right, the YAM in archaeology is used for Yamna. There's evidence, as shown here on the left-hand side, top left, that the Yamna people who originated, if we think, let me define a couple of areas. Here we've got what would be the modern Black Sea and the modern Caspian Sea. And the Yamna people from the Caucasus Mountains moved, as the arrows depict, as a function of time across Europe. And there's a lot that's been written about this, and chat with me during office hours if you want to get into some of the details, because a lot of it is pretty horrific as well. But what archaeologists, anthropologists, geneticists have been able to do is that they've been able to trace, using the genetic code, the expansion of peoples throughout this area. So on the lower left, each of these numbers represents time before now, years before now. So minus 10,800 years before today, minus 10,200 years before today. And if we go left to right, what I want you to see is the colors. And all I want you to see is that the colors change. So if we go back to 10,800 years before now, notice here in this top left image, the only colors that you see are shades of black and blue. If we move to today, we see all of these shades of yellow down into oranges, pinks, and red, with some sliver of black and blue on the lowermost part. And on the right here is an animation of how the genetic code has changed over the last 10,000 years. And what I want you to see is that it's like a wave. If we go back to the beginning, we've got all blacks and blues, and as time progresses, notice the wave of color from right to left. This wave of color is an indication that the Yamna people were moving from the steppes of Asia, the Caucasus Mountains, to Europe. And we can tie this to the evolution of trade routes for alloys such as bronze. So what happened? We then go from the Bronze Age to the Iron Age, and the Iron Age starts between about 1200 and 600 BCE, depending on where you are. So there's not an instantaneous change from the Bronze Age to the Iron Age. But what happens? We've got a combination of people of the seas, so we've got invaders coming in and destroying all of these cities. We also know that we have significant changes in climate. So those probably worked together to cause the transition from the Bronze Age to the Iron Age. But among the things that's interesting is that if we go back to the melting temperature of metals, and remember, copper melts at about 1100 degrees Celsius, so ancient humans had to add about 10% tin to the copper to lower the melting temperature enough that they could create a liquid, that liquid alloy we call bronze. Notice that the melting temperature of iron is 1500 degrees Celsius. So this is a WTF moment. If the ancient humans could not melt copper and they had to add tin to it, and by adding tin to copper they made bronze, and bronze is really hard, bronze beats copper, so we transition from the Copper Age to the Bronze Age. Why do humans go from the Bronze Age to the Iron Age if they still had the same furnaces that they used to make bronze, but notice the melting temperature of iron is way higher? What happened? How did they get there? Archaeologists have demonstrated that the most likely reason that humans transitioned from the Bronze Age to the Iron Age is that the trade routes, if we go back and we think of maps in this area, the trade routes that existed that allowed ancient humans to move tin and move copper around, the trade routes were completely destroyed. And as those trade routes are destroyed and humans did not have access to tin or copper, they transitioned from bronze to iron, which required some chemical refining in order to be able to figure out how to melt iron, which required much higher temperatures than melting a mixture of copper and tin. So a lot of people would say that it was because of need. In order to make bronze, you need copper and tin. You don't have copper and tin anymore because your trade routes have been destroyed. There's an abundance of iron, something we'll come back to in one of the subsequent lectures during the term. So let's figure out how we can melt iron. And that's what I'm going to show you a video of here now. And you'll see other things in the video that humans had to invent.
The earliest use of iron, however, was from native metal iron, but not from this planet.
Fly, space sword!
Several examples of early iron weapons and tools are found to be of meteoric in origin. This offered too small of a source to make any significant impact. The actual smelting of iron itself was a major roadblock that prevented any mass adoption of iron, But it's a discovery that didn't come out of nowhere, so let's trace the path we followed to be able to achieve this next milestone. Starting at the birth of humanity, the first step was learning how to master stone tools, allowing more complex tools to be made, and eventually learning how to process raw clay into ceramics, one of the most crucial discoveries made by humans. Then sourced the first form of metal used by humans, made of copper, and learned the properties of metals and how to shape and use them. Next, we learned the concept of smelting, where you can turn plentiful ores into the raw metal, using what was likely the first smelted metal, lead, that required nothing more than a hot fire. Then we applied this concept to copper ore and tin ore to alloy into bronze, using blowpipes to raise the heat of the fire to the necessary temperature. Then we also experimented with a draft kiln, allowing the temperatures to be maximized even further with a cob tower that allows a natural draft to form. Iron, however, requires an even higher temperature, with raw ore smelting into iron at around 2300 degrees Fahrenheit, bellows, which pumps large quantities of air to heat charcoal, maximizing our temperature to just high enough to smelt iron. Most recently unlocked. The earliest evidence of bellows are pot bellows. Ceramic bowls that are covered with leather and can be pumped up and down to force air into the kiln. Lauren got ours started by building the bottom shape of the bowl with cob on top of a mound of sand.
Wow. Yeah, bro. That was like the saddest brain. Alright, well, what now? Oh, that's sad.
Then repeat for the second bellow and make the tuyere tubes that transfer the air to the bloomery. To build the bloomery where the iron will be smelted, I used leftover stalks of sorghum from the crops that I grew last year. One thing I learned since our earlier cob kiln is that we should be using a much higher quantity of grass in our cob. This, with the form, made it a lot easier to build a really nice tall tower for the bloomery. While those dried, now ready to do our smelt, we moved our partially dried bloomery and bellows to the site of the smelt. First up, we cut open the hole at the bottom for the air to enter.
With a few good pats.
And then attach the tuyères to the pot bellows to direct the air into it. We also then finished up the pot bellows by building them up a little taller and added a lip to the end of them where we'll tie the leather onto it. Once the leather is attached, it creates a mostly airtight seal, pushing the hide up and down supply of air into the bellows.
It works.
Then everything was left to finish drying over the weekend.
Whoa. Your turn, Olivia. Yay!
Got the bloomery all built up, dried it out, and lit a little fire here to burn it out, and got the bellows them out, got them working. So now we're going to load it up. Got about a pound of charcoal and a pound of ground ore. Just going to do alternating layers of each, fill it up most of the way, light it up, and get pumping. Turn down now and see what we got inside. So we started at around noon, now almost 8. Should be enough time for it to have smelted, assuming we got to the right temperature, which it seems like we were. Having a hard time getting the bloom out to actually tell. And a lot of it clogged, kind of right along here in the ankle of the boot. I might have to break it out. There's bloom. A lot of the stuff that came down here, I think it's slag. It's more like glass. This part, I think, is pretty solid iron. The thing that's glowing here.
Wow!
So we put in like 35, at least 40 pounds of iron ore. Have a pretty decent bloom. Start breaking this guy up and see how much iron we have at the end. Looks pretty promising. So we got a fair amount of slag on the outside, but I think once we get inside, it seems to be pretty solid chunk in there. Hopefully we can make something out of it. Move on into the Iron Age. I made this. It's pretty hot still. At this point, we've now officially made iron and brought ourselves into the Iron Age. To actually start turning it into something, the next steps are breaking it up and starting to work the iron inside the bloom. Right now it's still mixed with a fair amount of slag, and by working the slag out and folding the iron into itself, we'll eventually create a workable piece of iron. But that'll be in an upcoming video. With this new metal, we have now officially entered the Iron Age. And one of the...
Alright, so let me walk back through that and just highlight some of the things that are important. Right? We go from the Bronze Age to the Iron Age. Why? Collapse of trade routes. In order to smelt iron, we need high temperatures. And so what they depict in the video is they first make what they call a bloomery, which you can think of, let's get to it, as a chimney. So here we've got this bloomery. And think about this. This was actually another technological innovation at some point in human history. And what's significant is they've made this chimney, which is referred to technically as a bloomery. And then they're also making the bellows. So she's making here the bellows out of clay and then allowing that clay to harden, to dry. One failure, but we know that success always follows failures. So she creates these bellows, and a bellow is a big open space. So they've got the chimney made out of mud or clay. They've got the bellows made out of clay. They've got these tuyères, which are essentially, these are open clay pipes. So you've got open space here and open space here. And then notice here I'm tracing over it with my cursor. That open hole is the open pipe that connects this space to the bottom of the bloomery or the bottom of the chimney over here. So we've got two bellows. And then they take animal hides or animal skins and put those on top. And then by raising and lowering and raising and lowering air, and air contains about 20% oxygen, they're pushing air into the bottom of the chimney. And again, oxygen plus charcoal equals energy or heat. So at the top of the chimney, up here, what he shows is mixing what he calls ore. And ore, right now, all I need you to know about ore is that's a rock here that contains iron. That's all I need you to know. So just think of ore is a rock, and that rock's got iron in it, and we need to get that rock to really high temperatures to cause the iron that's a solid to become a liquid. And the way that we get to really high temperatures is using charcoal. And what was done, at least to the best of our ability to understand how early humans did this, is a mixture of charcoal and iron ore at about 50-50, meaning 50% charcoal, 50% iron ore would be mixed and essentially stacked within the bloomery or within the chimney. And then by using the bellows, up, down, pumping more oxygen into the bottom of the bloomery, that causes the charcoal that's being poured to get to a really high temperature. And there's also some other stuff here, some redox processes, which we'll come back to. But that charcoal gets hot enough that it causes the iron as a solid in the rock to become a liquid. And at the end of this, remember they said 8 hours, right? Think if you had to do this for 8 hours, sit there and pump and pump and pump. At the end of the 8 hours, they end up having to take the chimney apart. And what they end up with is they end up now with this, and he used the word slag and iron, and slag simply means everything that's not iron. That's all I need you to know for now. We'll come back and focus on that and better define it in a future lecture. So now we've got, as he breaks this open, we have within that iron, and that iron can now be worked by taking that pure iron, putting it back into the bottom of the bloom, or here we've got the chimney, surrounding that with charcoal. That charcoal is combusted so that it's producing or liberating energy held between the carbon atoms in the charcoal. And that iron now, we started with iron ore, the rock had some iron. Now we've got this, which is almost 100% iron. We can get it hotter, and when we get it hotter, we can do what blacksmiths do, which is to work that iron, as is shown here, with a
This new
hammer.
metal, we have now officially entered the iron age.
And now we can make tools. Pretty sweet, isn't it? If you ever have the chance to blacksmith, do it. My wife took a blacksmithing class when she was in college, and she absolutely loved it. But we've gone from a rock that had a little bit of iron to now a tool that's 100% iron.
Of Michigan.
Pretty sweet, I think.
But across Africa.
So, one video here now to give you a sense of where this is happening.
But across Africa, in the lush forest of modern technological innovations, were laying the foundation for other civilizations. Sometime between 1800 and 1500 BC, small communities of craftspeople gathered to stoke furnaces, intending to fire ceramic. But in the lateritic African soil, the craftsmen discovered a byproduct, iron.
Iron is one of those inventions that actually has a tremendous impact.
We suspect the first usages were for decoration, for ornamentation, but very quickly people would hope, hey,
each metal has a certain quality, iron for its strength, and the kind of tools that one can create with it.
In terms of converting economies from hunting and gathering to agriculture, iron began to be used particularly, but also in production.
We previously thought that 100 BC, but knew at the same time in Africa.
For a long time, the idea that iron could be smelted in sub-Saharan Africa was completely dismissed.
the new evidence is that ironworking begins right in the heart of Africa. We find dates of around 1,000 in Lake Chad, get toward the middle of Nigeria, 700 to 500 BC over in Mali, showing the spread of iron coming out of that area.
Even with the kinds of technology difficult to produce a smelt in the way that people would have, 3,000 years ago.
People talk about civilizations, and they think everything new and exciting begins in a civilization. Turns out, when we look at history, human beings create advanced new technologies out of their own experiences. They don't have to live in this kind of society or that kind of society.
The iron-working communities of Central Africa left little tangible evidence of their existence behind, but they did leave their technological legacy, together with a sophisticated artistic heritage unique to this part of Africa. Near the center of modern-day Nigeria during the first millennium BC, a remarkable artistic tradition of terracotta sculpture emerged. These pieces are highly sophisticated, intricately detailed, and technically accomplished. Yet much of the culture from which they were created remains a mystery. They're known as the Nok terracottas, and they are sublime.
All right. By the way, that's a great series. One of my favorite historians, Henry Louis Gates. If you're not familiar with this, I think you can get them all online right now. Just an awesome series where he walks through Africa's great civilizations. And again, if you went through K-12 in the US, very Eurocentric history, you'll read a lot of what in essence is just patently false history, that there were no great technological innovations in Africa. Complete bullshit. So throughout Africa, there was an amazing amount of technological innovation. And I just wanted to show you this to remind you that when we think about the invention of bronze, we think about the transition from the Bronze Age to the Iron Age. It didn't happen in one spot and then move outward. At least it seems clear that it happened in different places independently. All right, and then what happened, right? So we go from stone to copper to bronze to iron, and then literally almost 2,000 years go by and we don't do anything until we get to what we call the Enlightenment or the Scientific Revolution, which are in the current era around 1700 for the Enlightenment and around 1550, 1600 for the Scientific Revolution. And what was significant then, I'm going to show you a video just to get you excited. Stand up and do some jumping jacks as you watch this.
I'm Grill B, and this is World History Wednesday. Today, I'll be teaching you about the scientific revolution. Pay attention, take notes. The Renaissance influenced by the Greek, Ptolemy, who created rationalism, and this is the belief that common sense and logic will explain all that you see. Fast forward to 1543. A man doubted these teachings from the 2nd century. Greeks said that the sun wasn't the center of the universe, it was Earth. This is known as the geocentric theory. This Prussian scientist named Copernicus said heliocentric planets went around it. It was an intriguing notion, so the German Johann Kepler observed the planetary motion. He saw the planets orbit sun in oval revolutions. But get those Greek ideas, homie, this is a revolution. And here's the resolution. Aristotle was right. Psych! Galileo, the Italian mathematician who improved, and with it he saw Jubilee Eden. He was peeking at the moon and saw the surface was uneven. This contradicted teachings Greeks were preaching. Aristotle was right. Psych! Aristotle got it wrong. Copernicus was right. Galileo got involved. He disproved Aristotle just by dropping 2 balls. Think about it. If I took a bowling ball and a tennis ball and I walked them up to a 3-story building and I dropped the balls at the roof at the same time, raise your hand if you think the bowling ball will hit the ground first. Raise your hand if you think the tennis ball will hit the ground first. Okay. If your hand was raised, you got it right. Psych! You got it wrong. Back to Galileo. In 1616, he's beefing with the Pope. The church said stop teaching heliocentric, but he didn't listen. 1633, he brought in voted inquisition, charged him with heresy. And this means apparently he contradicted what they taught. Church was really scared that the people who were hearing Galileo's observation would see church was wrong all along, and they couldn't take it. They forced him to lie and say he wrong in the statement. Yeah, the church was hating male cow defecation. The Pope was right. Psych! The Pope got it wrong. Okay, Isaac Newton was sitting down under a tree. What did he see? An apple fall to the ground rapidly. That's gravity. Earth's pool of objects. FEA. Force times 9.8 meters per second squared. Its effect is clear. What's the lesson here? Logic gives you ideas, but you got to test them here. Rational thought isn't always what it seems. If we listen to the Greeks, you wouldn't believe in gravity. Aristotle was right. Psych! Aristotle got it wrong. Okay, British Francis Bacon introduced that unique conclusive proven back to prove your posture on the problem is the truth in that. Observations proven to enact to be exact. Posture is hypothesis, you gotta prove it's true with facts. This is scientific method that you start using to do hard science projects off the chart. Thanks to Bacon and Descartes, who turned investigation to an art. Scientific revolution. We all right.
All right, I know some of you are thinking, what the heck does that have to do with this class? But gave you a couple of minutes, you didn't hear my voice, and I just wanted you to think about what happens in the 1500s, 1600s, 1700s. We go from those 7 metals of antiquity, which we read about in the Old Testament. We go from the copper to the bronze to the Iron Age, and then we go literally a few thousand years with seemingly nothing, until we start to hit the 13th and 14th centuries. And humans started figuring out how to physically extract elements so that they would exist by themselves. So remember, with copper, the Copper Age is where humans found native copper and could just hammer it into tools. With bronze, humans figured out how to take that native copper, mix it with tin, 90% copper, 10% tin, melt that at a high temperature, produce bronze. Then humans figured out how to mix iron ore with charcoal, get that to a high enough temperature using a bellows to pump oxygen into the charcoal to create high temperature. We could melt the iron and then we could use that iron to make tools. and then nothing for almost 2,000 years. And then all of a sudden, boom, Enlightenment, scientific revolution. When we think about people like Galileo and others and all of the scientific innovation, we now start to see that happening with respect to chemistry. So in the 13th and 14th centuries, humans figured out how to isolate arsenic, antimony, zinc, and bismuth. Hadn't been done before. 15th century, nothing. 16th century, the only metal for which we have evidence humans figured out how to separate and purify is the metal platinum. That's it. Then we go into the 17th century, nothing. 18th century, look at all the metals that humans figure out how to extract from rock so that the metal exists in its pure form. We get metals like cobalt and nickel, manganese, molybdenum, tellurium, tungsten, uranium, zirconium, titanium, yttrium, beryllium, chromium. You don't have to memorize these. Then in the 19th century, it's like we jumped on the treadmill and took steroids and started figuring out how to purify all of the elements that make up the modern day periodic table, from niobium down to actinium. And then in the 20th century, we round that out with the last few elements that we purify from the rocks in which they're contained. And I want to just go backwards in time, because when you look at this, honestly, for all of you right now, your demographic, all the way up to me and your parents and your grandparents, you look at this and you think, who cares? But look at what happens here if we look at this as a time lapse. If we build out the periodic table, okay, starting in 1718, and the years are climbing up, 1730, 31, 32, 33, 34, 35, 36, 37, 39, 40. What you'll see here are the metals and the year that they were discovered. Right? And remember that we didn't have the periodic table until the late 19th century, the late 1800s. But look at how fast we went from the 7 metals of antiquity to the 92 elements, the 92 naturally occurring elements that make up the periodic table. Or in reality, the periodic table is simply the human construct that allows us to organize on their electrochemical and physical properties. But it's fast, right? We don't think of this as fast when you look at the clock here and you think 300 years of it. But in those years, humans went from those 7 metals of antiquity to 92 naturally occurring. And what's significant of this class is we then figured out how to use all of those elements to make stuff. Right? And remember, if we think about the original copper tools in the Copper Age, and then we alloyed copper and tin to make bronze, the reason that we made bronze, the collective we, is that we could make bronze stuff. And then we figured out how to smelt iron ore. And why did we want to smelt iron ore? So we could make iron stuff. And today we've got these 92 naturally occurring elements, plus we have a couple of dozen synthetic elements that have only been made in scientific experiments. But in terms of human history over millions of years, that was literally overnight, is how fast it happened. And here we are today. So every one of you has, I'm guessing, some kind of a smartphone or a cell phone, no matter what the brand is. And when you look at your cell phone or smartphone, most of you probably aren't amazed. This is a picture I took. This is my younger daughter, Laura, and my grandmother, who passed away a couple of years ago, just shy of her 100th birthday. She was born in 1918 in a small village in what is now Slovakia. And when she was born, there was nothing by way of technology in her village. There was no running water. There was no plumbing and piping system to get rid of waste. They had an outhouse. There was no radio, no refrigerator. My grandmother tells a story about her brother in the early 1920s bringing the very first radio to their village. And it had this huge long antenna. And everybody from the surrounding area came and just watched through the window when her brother, using a battery, because they had no electricity lines, he used a battery to start up the radio, and from that radio, magically voices would talk, and everybody was blown away. And this was a few years ago when my younger daughter was showing my grandmother what was then, I think, an iPhone SE. And my grandmother was just blown away, absolutely blown away at this technology. And what I want all of you in this class to do is I really want you to get into the mindset of how technologically advanced we are as a civilization today. Doesn't matter the language we speak, doesn't matter if we pray to a God or not, but collectively as a society globally, think about how much we have advanced from the Stone Age to the Copper Age to the Bronze Age to the Iron Age to whatever you want to call today. The iPhone age, the Samsung age, the technology age, the digital age. We've come a long way. And when you think about a smartphone, right, pick yours up. It's probably close to you, right? On average, we pick up our phones probably 100 times a day, if not more. When you hold your hand, when you hold a smartphone in your hand, how many of the elements in the periodic table are in your smartphone, right? We go back and we read the Old Testament and we find 7 metals of antiquity. That's it. And then it's the 13th and 14th century, 2,000 years later, where we start to see humans develop the ability to separate metals like arsenic from the rocks that hold them. Until we get to a smartphone and we get to modern technology, it turns out that there are about 70 different elements in the periodic table in your smartphone. 70, right? There are 92 naturally occurring elements, and about 70 of them are in your phone. So I'm going to play a video now that's a few years old. The Kardashian reference at the end is probably no longer appropriate, or at least I don't think the Kardashians are as popular as they once were. But I just want to give you a sense here of how amazing a smartphone is with respect to what it contains.
The lines are probably already forming for the new iPhone 6. After months and months of rumors, we finally know what it'll look like, what kind of horsepower it's packing. But how much do you really know about that piece of technology in your pocket? For instance, a typical smartphone contains about 300 milligrams of silver and 30 milligrams of gold. The gold and silver used to manufacture our phones this year alone are worth more than $2.5 billion. Our friends over at Compound Interest pulled out the periodic table and identified dozens of other elements that are also packed into your typical smartphone. You can't do anything on your phone without a battery, and that power source is most likely a lithium-ion battery. Those batteries use lithium cobalt oxide for the cathode or positive side, and carbon or graphite for the negative side, called an anode. The anode produces electrons, and the cathode absorbs them to produce the juice that powers your phone. Some phone batteries use manganese in place of cobalt, and almost all phone batteries, and often the entire phone, are encased in aluminum. It may look like a piece of glass, but that smartphone screen actually contains some of the rarest elements on Earth. Very small quantities of things you've probably never heard of. Sexy elements like praseodymium, terbium, yttrium, and gadolinium help produce the colors on a smartphone screen. Apple has bragged about the iPhone 6's ion-strengthened glass, but what does that really mean? It's actually a simple chemical process. In at least one method, the glass is dipped into a bath of hot potassium sulfate. This causes the sodium ions in the glass to migrate, and the larger potassium ions in the bath squeeze themselves into the holes left by sodium. This compresses the glass and makes it stronger. Finally, a compound of indium, tin, and oxygen actually puts the touch in touchscreen. Those three are used in a transparent film that conducts electricity so the touchscreen can function. Alright, smash your phone open and you'll see another hidden chemistry world. Go on, do it. I'll wait. You done? Good. Copper is used for wiring in the phone, as well as the tiny microelectric components. Engineers also use a metal called tantalum to make tiny capacitors. Capacitors store and regulate electricity and can dump their electrical charge in a fraction of a second, unlike a battery. Of course, silicon is used to make the microchips in the phone, the brains of the whole operation. In the chip, it's combined with oxygen, antimony, arsenic, phosphorus, and gallium to produce a highly conductive, powerful chip, which then you can use to play that stupid Kim Kardashian Hollywood game or whatever. So there you have it. The elements that make up the thing you can't put down.
All right, so clearly the iPhone 6, that was a bunch of years ago, 2013, 2014. And hopefully nobody broke their phone. But what I wanted you to see there, and again, you don't have to memorize every detail of that video. What I want you to see is that when you pick up your smartphone, you've got all of these elements in your smartphone. And as a species within the animal kingdom, if we go back 6,000 or 7,000 years, all we used were stones. We literally used stones. That was it. Then we found native copper. We could use the stones to pound the copper into tools. We made copper tools. Did that for 1,000 plus years. Then figured out, whoa, if we mix copper and tin, we can melt it. We can make bronze. Then we have a combination of people of the seas and climate change, drought throughout the Mediterranean and the Middle East. We completely eliminate the trade routes that allowed humans to get the tin and get the copper. We go into the Iron Age, and all we used was iron. And then during and after the Iron Age, we continue to use bronze because we reestablished trade route by war. And then fast forward, now we have the smartphone, right? I want all of you, every single one of you, just to take a second, and I want you to say, wow, holy moly, that's awesome, unbelievable, right? If you're like me when you took chemistry in high school, I couldn't stand chemistry because I couldn't see how chemistry was relevant to me. And then I got to college and I took chemistry and figured out, wow, chemistry is pretty cool once I start to figure out and appreciate how we can take all of these natural resources and chemically manipulate them so that we can make the stuff that makes us modern humans. And all of these elements, as I said, you don't have to memorize them, all of these elements are physically in that smartphone in your hand. Now, they talk about the touch screen, and I'm just going to play a couple of seconds here because the touch screen should blow you away. Honestly, the fact that you can pick up your phone and just move your finger around on the screen, let's just take a quick look.
Capacitive touch technology. Right, let's take a closer look. Let's peel back the layers of the screen. The top layer is the protective cover. In modern smartphones, that's pretty much going to be Gorilla Glass. Now, that's not glass made of or by gorillas, but it is ruddy strong. But for all its technological might, it's essentially made from sand, which is exactly the same way that we have been making glass since way back, probably at least the ancient Egyptian time. So you take your sand, which is silicon dioxide, you mix it with a few other chemicals and you melt it down. The glass you get is known as aluminosilicate. Then you need to give that a wash in a potassium bath. All it essentially does is it rips out the sodium ions and replaces them with potassium ions. And that compresses and strengthens the glass. Voila! Gorilla Glass. Now, underneath that protective layer is where it gets interesting. There are two layers that are covered in electrodes that are thinner than a human hair. One of those layers contains what's known as the driving lines that carry and the other one contains that sense the amount of current and charge being carried by the driving lines. They're perpendicular, they're right angles to each other. Now, when you move your electrically conducting stubby finger down towards the screen, it changes the amount of charge in those driving lines. When you actually touch the screen, some of that chuck to your finger, and it's the job of the sensing lines to pick, which is why you can't operate your smartphone wearing gloves unless they're fancy conducting gloves, because it...
All right, so I don't want you to think that you have to memorize all this technology, but again, this stuff blows me away, honestly. At my age, when I was your age, there was no cell phone. In fact, when I was a senior in college is when I got my first email address. And again, what I want you to do, when you pick up your smartphone, at least swipe across and say, that's pretty amazing, and recognize that your ability to break that conductive charge, as he described it, that only happens because if you look at this lower right here, One of the layers that makes up the screen in your smartphone, one of those layers shown here between this person's thumb and fingers, is a mixture of tin, indium, and oxygen, the same exact tin that in the ancient world humans mixed with copper to produce the alloy bronze. Today we make an alloy of tin and indium and oxygen, which allows us to make this transparent layer within your smartphone where we can move current or electricity, and by touching it, we can change the circuitry. Now, I know for some of you who are big tech fans that this has changed in the last couple of years, but just run with it. Just accept that this is what we do, and it's by using these metals. And again, what are we doing? We're making an alloy, just like the ancient humans made bronze. And then you break down your phone and you think about all the other resources that go into your phone, right? We've got 70 plus inside your phone, and this is just a snapshot of some of them. Your phone has arsenic, it has copper, gallium, gold, magnesium, palladium, platinum, silver, tungsten, and it has byproducts from oil. Natural gas is used as part of making the plastics. Oil is used as part of making the plastics. And all I want you to see here, just to give you a sense of the future in this class, I mentioned humans and the invention of trade routes, right? We had to source tin from the cassitarides and bring it all the way back to ancient Greece to mix with copper that we could get from elsewhere in the Middle East. When you look at your smartphone and you think about all these metals, this is where they come from. The arsenic in your phone comes from China and Chile and Morocco and Peru and Kazakhstan and Russia, Belgium, and Mexico. Where does the copper come from? From Chile, from the United States, Peru, China, Australia, Russia, Indonesia, Canada, Zambia, Poland, Kazakhstan, Mexico. The trade routes have gotten bigger. Now we have trade routes that truly circle the entire globe. And a major focus in this class is going to be assessing and understanding how trade routes have evolved. And ultimately, trade routes are driven by humans who want something that we don't have locally, and we have to get it from someplace else. So when we think about smartphones and we think about their proliferation around the world, the penetration rate of smartphones, as of 2021, there are almost 4 billion smartphone users in the world today. So more than half of the people on Earth, slightly more, have a smartphone. And if we think about people that have a smartphone and a mobile phone, and in a lot of developing countries, people have what we would think of as an archaic mobile phone, it's about 5 billion people that have a mobile phone. Now, if we go back 100 years, the number was 0. So we literally went from 100 years ago, nobody had a smartphone, and today we've got 4 to 5 billion smartphones and mobile phones on the planet. And for all of you, I'm guessing all of you have at least a smartphone. Certainly it operates as your mobile phone, and you might have other stuff, right? So this is a figure here that just gives you a sense by age, right? The percent of US adults, so this is specific based on surveys of US adults, who say their household has 3 or more of these electronic devices. And within the age group 18 to 29, right, we can see how many devices you report you have. I've met a lot of students who have a smartphone, they have a tablet, they have a laptop, and then they may have other things. They have a smart watch that allows them to get their email by simply looking at their wrist. Think about this compared to the ancient Greeks, the ancient Chinese, the ancient Assyrians, the ancient Africans in Chad and Niger and Mali. And think about what is labeled here, the accelerating growth in technology. At some point, K to 12, you learned about the printing press. So if we go back here, this is a simple graphic that shows us years on the x-axis. So if we go back, we had the printing press, which was invented about 600 years ago. The telescope was invented about 300 years ago. The steam engine, the light bulb, The car was only invented about 100 years ago. And then look at what happens. Within the last 100 years, whew, look at how much technology we have invented. And all of that technology, which we can think of as stuff, is built from resources. And this class is going to focus on how we find those resources and manipulate them to make the stuff that is embedded throughout modern society. So on the bottom here is this map I showed you earlier, and I highlighted each of these areas that was a place on Earth, on the map, where early humans in Mesopotamia and Anatolia and moving across into Persia and across into the Himalaya, into China, parts of Russia, Europe, these were places where we found the tin and the copper and the silver to make stuff. The map up at the top, every one of these little dots that's a different color is a place on the planet where right now, as you listen to me, humans are digging out resources to make stuff. And all of these places here on the map on the top are connected by modern day trade routes. Now, I want to round out this first lecture, and I want to make a few points towards the end. Some of you may be familiar with the United Nations based in New York, and these are a snapshot. This is a graphic that indicates what are called the United Nations Sustainable Development Goals. And I'm going to go ahead and tell you that the word sustainable is really hard to define. We'll come back to that, but nonetheless, here we have these Sustainable Development Goals that are for the entire world to have no poverty, the entire world to have no hunger, everybody to have good health and well-being, everybody to have access to education. And by everybody and everywhere, I truly mean all 7.5 billion people on the planet. Clean water and sanitation, affordable clean energy. The point I want to make here is that the only way that we can achieve the UN Sustainable Development Goals, the SDG, is by extracting resources and manipulating those resources the same way early humans manipulated tin and copper to make bronze, the same way that modern humans manipulate 70 elements to make a smartphone. We're going to do that to change how we live, to change modern society. If you look at the Green New Deal, and in discussion, you're actually going to focus on and you're going to read about the Green New Deal and write about the Green New Deal. The Green New Deal calls for 100% of the energy that we consume in the United States to be replaced with renewable energy, like wind turbines and solar panels and batteries. And I'll tell you, those do not grow on trees. I've been to a lot of apple orchards, I've picked peaches, I've picked pears. I've never found a row of trees where there's a wind turbine growing, or a solar panel growing, or a battery growing. Those are all products that are manufactured or they are made by extracting elements that we think of as natural resources and manipulating them to make a wind turbine, to make a solar panel, to make batteries. And just like I showed you for cell phones, when we think about what we need to make wind turbines, we've got a similarly long list. We need crushed stone, bauxite, clay and shale, coal, cobalt, copper, gypsum. We need iron ore, the same iron ore that early humans smelted into the Iron Age. We see the same thing for hybrid cars and all-electric cars. They don't grow on trees. All of these require the resources shown here and many more. This is just a snapshot. And think about the trade routes. Jump over here with me to the right-hand side. The element sulfur. The element sulfur is used during the production of an electric car or a hybrid car or any car for that matter. And we mine or extract sulfur, and notice where we get it. In the United States, from Canada, from China, from Russia, from Japan, from Saudi Arabia, Kazakhstan, Germany, the United Arab Emirates, the Republic of Korea, Mexico, Chile, Iran, France, Poland, India, Australia, Italy, Kuwait, Finland, Spain, South Africa, the Netherlands, and Uzbekistan. So if you're driving a Tesla, you're driving a Prius, wow, You're literally sitting in a vehicle, and among the resources that humans extracted from the ground and used to make your vehicle is sulfur. And this is a snapshot of the places around the world that are on that trade route. We see the same thing for solar panels. Long list of resources. They don't grow on trees. So, this is where, when I teach this class in person, I love to stop and I love to look around the room. And I always tell students, I can look at you and I can look at your face at this point in time, and some of you are having an oh shit moment, like, oh shit, I thought solar panels were green and had no negative impact on the environment. But now I can see that a solar panel requires lots of resources, and all of those resources have to be extracted and mined in order to make my solar panel. I love my Tesla, and I thought that my Tesla had no negative impact on the environment. This is one of the themes of our class. In order to have any of these technology products, any of them, doesn't matter what it is, if you don't want to live naked in a cave, you want to be part of modern society and have access to all of these technology products, that requires extraction, which is a synonym for mining, in order to produce them. And one of the things I hope to give you a better sense of over the course of this semester is that we as a society, we can sustainably extract and make available all of these resources for humans to use to improve the quality of life everywhere for everyone. But we have to do it in such a way that we minimize environmental degradation, meaning that we do not degrade the environment as much as is only necessary to extract all of these resources to make the stuff that we have all become accustomed to using. Now, this looks like a busy slide, and I promise you we're getting to the end of this lecture. All I want you to take away here is that this slide shows you what has been called the growth of stuff. And stuff means everything that humans have produced. We extract or mine resources and produce things. The metals in a smartphone, the asphalt that we use to drive on, the bricks that we use to make houses, the aggregate or the gravel that we use under the asphalt, under the concrete to make our roads, the concrete that we use to make our buildings and our sidewalk, everything else, plastic. Plastic comes from oil. All of this stuff, if you add up the mass or the weight on the right-hand side over here, the left-hand side, sorry, if we add up the mass of all of the stuff that we've made, all I want you to see is that if we go back to the year 1900, the weight of all of the stuff humans around the world had made is down here, and the weight of everything biologic in the entire world, everything that's alive, you, me, all the plants, all the trees, all the animals, everything that's alive, grass, everything, is up here. And over the last 120 years, the total weight of biomass, let's say it's effectively not changed. Notice the weight of our stuff. Starts to climb. World War I, Spanish flu. By the way, the Spanish flu started in the United States. Keeps on climbing. World War II, keeps on climbing. 1960, starts to move up. Keeps moving up, 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 up. And right now, in 2021, if you put everything that humans have made, meaning resources we've extracted, manipulated, and produced something with, all of those things, all of that stuff weighs more than everything else that's alive on the entire planet. And the colors here, as the legend shows, the colors are for the different things, okay, different types of stuff. This anthropogenic mass, anthropogenic means human or human caused. So we'll also in this class talk about anthropogenic climate change. Here, anthropogenic mass is all of the stuff that we've made. I want you to have a WTF moment, because in 1900, here's the weight of the stuff compared to the weight of everything that's alive. And today, the weight of our stuff is more than everything that's alive, which means that we as a society around the world have extracted a lot of resources to make a lot of stuff. And where does it go, right? When we think about environmental degradation, there's not only the environmental degradation that occurs during extraction or during mining, which is something we will discuss in this class. There's also the environmental degradation that happens at the end of life of all of our technology products. So for example, when your cell phone dies, what do you do with it? Do you throw it in the trash? Do you recycle it? On the left-hand side up here, this is the back of a gigantic truck about the size of the trucks that you see that spread salt on the Michigan roadways when it's going to snow. All of these are cell phones. Where do they go? If you look at the top right here, these are all computer screens, massive computer screens, televisions, all electronic stuff. Where does it go? We'll also talk in this class about what is called here on the lower left e-waste or electronic waste, which is something that I have a lot of interest in trying to understand and has been referred to, as this graphic indicates, as an epidemic. We go from the first generation iPhone, iPhone 6, iPhone 7, iPhone 8, iPhone 10, iPhone 11, iPhone 12, and the same sequence happens with Samsung and Huawei and all the other companies that make cell phones. And all of those cell phones, they exist for a finite amount of human time, and then we get rid of them. I get rid of them myself. I have an iPhone 11. My wife has an iPhone 11. All 4 of my kids have iPhones, right? I mean, we are a super bougie family. We've all got iPhones. We all think we need them all the time. We need to stay connected. I need to get emails from students on a Thursday night and be able to respond right away because the students on the other end of the email don't know how to finish the assignment. So we'll talk about the negatives. I want to make sure that coming out of the first lecture, you all know that I'm not going to sugarcoat anything in this class. Everything is on the table. We're going to bring into this class race, religion, equity, diversity, inclusion, environmental degradation, mining, colonialism. Everything is on the table. In terms of e-waste, I would call it, I was blessed, the great pleasure of working with a couple of former Michigan undergraduates, Jason Toway here on the left and Ann Canavati here on the right, 2 superstar undergraduates. Jason was a pipe major and Ann was a triple major, I think Ann had 3 majors, like Near Eastern Studies, Arabic language, and international studies. Anyway, the 3 of us traveled to West Africa and we did a research project focused on electronic waste, which we'll come back to later in the class. I worked last year with a couple of other undergraduates, Roland Amartifo here and Madeline Carter here. Madeline was a sociology major. Roland was a pipe major. I think Roland right now is a graduate student in SEAS, the School for Environment and Sustainability. And here's the dilemma, right? We want the smartphone. Why do we want the smartphone? Because we think we need it, and because it also gives us access to the world, but we know it can cause significant problems at the end of life. We know that we need technology if we want to empower the entire world, and the project that Roland, Madeline, and I worked on was specifically focused on how technology in developing countries, and specifically we worked in the eastern part of Ghana in the Volta region, how can technology in the classroom, meaning computers, smartphones, tablets, connected to the internet, how can that be used to enrich the lives of female students, right? If we want female students around the world to be able to achieve the education that we consider standard in developed countries, then technology has to be part of that. But we know technology requires 60, 70, 80 metals. So we know we have to mine those metals, but we also know that there's going to be environmental degradation. So it ain't a black and white issue. It's like Whistler's Mother, one of my favorite paintings. It's an infinite number of shades of gray, which makes it really hard. And when we think about us, the collective us, you and me, and everybody else on planet Earth, and we look at where we came from, and we look at where we have moved over the last few 100,000 to possibly more than 1,000,000 years, we know, or we think we know, to the best of our ability to understand ancient humans, that we all came out of ancient Africa, and then we migrated. 60,000 years ago, the first humans leave Africa. They move across northern India. They move through Southeast Asia. There's evidence, if we look at Aboriginal DNA, that they reached Australia by at least 50,000 years. We know that we had other groups of peoples that moved across Asia, and at least 15 to 20,000 years ago, they migrated across what we think of as an ice or a land bridge across Russia to Alaska, or they migrated by boats. We know we had people moving to far northern latitudes in Europe. Okay? And here we see them moving far northern part, Asia and Europe. We see them moving into the Iberian Peninsula over here. And what drives this? Fundamentally, what drives humans is the need for, I've said stuff, but it's the need for food. It's the need to move because of climate change. So if we go back 25,000 years, all of the white on this map, these were all massive glaciers that covered up a significant portion, in this case, of Asia, significant portion of China. All of Russia was covered by glaciers. And similarly, we had massive glaciers covering Europe, all of Canada. And what does that do? It drives us to move. So humans have always been moving. We moved within Africa so that we could find the resources necessary to sustain our lives. With climate change, we moved to find tin, we moved to find copper, and we're still moving. When we think today in migration, we know that climate change is having devastating effects. For example, in parts of Latin America, Central America, we see massive changes in the ability to grow crops in this part of the world, which is causing a human migration north towards the United States. We see in the United States that we see climate change impacting the types of crops we can grow. And this is us today, right? This is our world at night. So we've always been moving, and resources are among the primary reasons that we move. So in this class, I want to open your minds up to how amazing the modern world is, on average, not for everybody. We're going to talk in this class, and in the textbook, we use the terms more developed countries and less developed countries, only specifically focused on technology, with no implications whatsoever to the people who live there. The more developed countries would be countries where we can go to Best Buy and buy a smartphone. Less developed countries are places where there is no Best Buy on every corner. There are not Chick-fil-A's and Burger King's and Meijer and Publix and Winn-Dixie's and Safeways that have an abundance of food that we can buy. I want to open your minds up to the fact that we all use resources. Tree huggers use resources. People that are conservative use resources, right? It literally links all of us together. Doesn't matter how you vote, doesn't matter if you vote, doesn't matter if you pray, who you pray to, doesn't matter what pronoun we choose. All of us use resources in ways that we have never actually thought about before. And my goal in this class is to make them come alive. So, rounding out lecture 1, look at where we were and look at where we are. And look at how fast, literally in the blink of an eye, born with no electricity, no modern plumbing, 102 years ago. And today, we take for granted, without saying that's a negative thing, we take for granted our access to stuff. All of the stuff that makes modern humans modern. We went from that stone fire. We manipulated native copper. We alloyed copper and tin. We broke apart the trade routes by war. We still have trade wars today that disrupt trade routes. We then rounded out the periodic table in the 17th, 18th, 19th, and 20th centuries. And today we have all of the technology that makes society what we know. And we take it for granted. So when you look at what we've invented, 1827, the first photograph, all of you have a smartphone that can take photographs. The first typewriter, 1868, sweet mama. First telephone, look at that telephone compared to your smartphone. The first radio, look at that. Airplane, 117 years ago, 118 years ago. The first Model T. So think about what we have today. I don't want you to take it for granted. I want you all to wake up every single day and just have a little bit of an appreciation for how absolutely amazing life is today for most people. Now, I want to highlight that. Most people. Life ain't awesome for everybody. It ain't. Life is not awesome for some people in Detroit or Chicago or Ann Arbor. It ain't awesome for some people in Ghana or Nigeria or Russia or China or Brazil. On average, it's awesome for most people in more developed countries. And if we want to achieve the United Nations Sustainable Development Goals, if we want every boy and girl in every country, on every continent, to have what we think of as normal, that's going to require strategic extraction of resources, meaning mining of new resources, and also figuring out how to do that